In this video, we're going to be going back to our discussion of systems of coupled second-order differential equations and a new way of representing them and analyzing them mathematically that we're going to call state space representation. So we have here this example of a coupled second-order set of differential equations or set of second-order differential equations. And from what we've seen in previous videos is this can be rewritten in a form of m x double dot plus b x dot plus k x equals some capital F of t, where m, b, and k are matrices, x dot, x double dot are vectors, and f is also a vector. And what we also did in the past is we said in the special case where b is equal to 0, where there is no damping, then we can do a type of eigenvalue analysis on this system. But if b is non-zero, then the eigenvalue analysis becomes much more difficult. That we get what's called a quadratic eigenvalue problem, which is not something that we necessarily want to be dealing with. So we introduce what's called state space representation to make the analysis simpler, where instead of doing, in this case, a 2 by 2 with a quadratic eigenvalue problem, we expand it by making it a system of 4 first-order equations, and we do a regular eigenvalue analysis on a 4 by 4 matrix instead. And so the way we do that is by defining a new vector y, which is equal to x and x dot. And that's going to be equal to, in this case, x1, x2, x1 dot, x2 dot. These are the lowercase x's, where they're just the numbers, whereas in this one right here, these are capital X's, and we're dealing with vectors. And with these differential equations, we're going to put it in the form y dot is equal to some matrix A times y. So what we need to do is isolate these, or the derivatives of this vector right here. So y dot is equal to x1 dot, x2 dot, x1 double dot, x2 double dot. So let me go real quick. I'll copy these equations down in the bottom. So these are the equations that we're dealing with. And what I can do is I'm going to just go ahead and isolate x1 double dot and x2 double dot. So oops, x1 double dot is going to equal f of t minus 10 x2 plus 10 x1. I'm distributing the 10 into the x2 and the x1 right now. And then minus 3 x2 plus 3 x1. And the whole thing is divided by 5. x2 double dot is going to equal minus 10 x1 plus 10 x2 minus 3, sorry, x1 dot, there should be dots up here as well, plus 3 x2 dot, and the whole thing is divided by 2. And so here, y dot is equal to x1 dot, x2 dot, x1 double dot, x2 double dot. So we've just isolated the terms that are going to go in these second two entries right here. So, and this is going to have It's going to be a matrix multiplied by x1, x2, x1 dot, x2 dot. And so we're trying to relate these terms here to these terms here via a matrix. So x1 dot and x2 dot are already in this matrix. So the first row I can just say 0, 0, 1, 0. x1 dot is equal to 1 times x1 dot. And I can go 0, 0, 0, 1. x2 dot is equal to x2 dot. For x1 double dot, the x1 term is going to be right here. It's going to be 10 over 5 times x1, so it's just going to equal 2. X2 is minus 10 over 5 minus 2. X1 dot is 3 over 5. And x2 dot is minus 3 over 5. We still have this f here, which I'll get to in a second. But let's go ahead and move on to the x2 double dot. So x2 double dot, the x1 term is minus 10 over 2, so it's minus 5. The x2 term is 10 over 2, so that's 5. Yeah. Okay. The x1 dot term is minus 3 over 2. And the x2 dot term is 3 over 2. So now we have something that looks like y dot equals a times y. And this is the homogeneous term. But we have to add on that f of t, so we're going to get something where x1 dot is just equal to x1 dot, x2 dot is just equal to x2 dot. X1 double dot has a f of t over 5. Let's just do this. It's going to be 1 over 5, or yeah, just 1 over 5. And x2 dot doesn't have anything. And this is all multiplied by f of t. And that we often just say is equal, we just add a g times f, where g is this vector right here. So this is state space form. A, or y dot, is equal to ay plus g times f. And the book presents that we can write it in a more general form. So book presents it this way, and this is algebraically the same, where you've got some block matrix where you have an identity matrix, a zero matrix, and your mass matrix. So this is the same mass matrix that would have come from right here. And this is multiplied by x dot, x double dot, equals the zero matrix, the identity matrix, minus your stiffness matrix, minus your damping matrix, times x dot, plus 0 g. So this is so this g comes from your inputs times some force. And we're going to call this matrix here m hat. We'll call, so this is the y dot matrix. This matrix we'll call k sub b hat. This matrix we'll call, so this is the y matrix. This is g hat, and it's defined by your inputs. But this is the general form of state space. And if we write this, m hat y dot equals kb hat y plus g hat f, we can use techniques of linear algebra to find the solution y of t. We can figure out what this system is going to be doing in time. So let's look at just the homogeneous case. So we'll say this is equal to 0. And we'll assume the solution y homogeneous of t is equal to u e to the pt. And so if we plug that in, y dot, or if we take the derivative of that, y dot is going to be u p e to the pt. And we can plug that in. So m hat u p e to the pt equals kb hat times u e to the pt. And if we do a little bit of moving around in algebra, we'll have minus p m hat plus kb hat, multiply that by u e to the pt equals 0. And at this point, we're looking at another eigenvalue problem. E to the pt is never going to equal 0. And so p is going to be our eigenvalues, and u is going to be our eigenvectors, I'll call it e. And if we do that, then y of t is going to equal, like we already said, ue to the p or lambda t, which if we have a 4x4 system, that's going to equal the vector e1, or some constant times the vector e1, e to the lambda 1 t plus c2, the second eigenvector times e to the second eigenvalue times t plus c3, the third eigenvector times e to the lambda 3t plus c4, fourth eigenvector, e to the lambda 4t. And that's how you would solve a coupled system with damping using state space representation. And we'll end that video there.